Hello everyone and welcome back. Now, the past 3 lectures we've used separation of variables to solve the one-dimensional heat equation. What I'd like to do in this lecture is solve a 2-dimensional example. So first of all, let's remind ourselves what the 2-dimensional heat equation looks like. And again, just in a very, very simple context. Here we have what's called the Laplace operator. So if I remind myself what this looks like, it's the sum of second order derivatives in space. In my case, 2-dimensional domain, I'm going to consider myself on a rectangle. So here I would like to have 0 less than or equal to x, which is less than or equal to L, and 0 less than or equal to y, which is less than or equal to h, length and height. Now, here's the thing. I could solve this using separation of variables. You're going to have 3 complicated terms in here. But what I would like to do first is I'd like to just solve what's called the Laplace equation. Okay, so I'd like to, instead of finding a time-dependent solution, I want to solve this thing equal to 0. So what I'm doing here by solving Laplace's equation, right? So solving, the k can disappear as well, since it's just a constant. I'm setting the second order derivatives in space, the sum of them, equal to 0. Now think back to what we did with the equilibrium temperature distribution. We were essentially solving the second derivative equal to 0, right? And we applied different boundary conditions, and we saw that solutions are really simple, and a lot of times they're unique. Well, it turns out that solving the Laplace equation in higher dimensions is a very, very difficult task. This forms the basis of what's called harmonic theory. So the solutions to this, turns out there's infinitely many. They are extremely dependent on what domain you have, and they're extremely dependent on the boundary conditions of the domain. But you should remind yourself that these harmonic functions, solutions to the Laplace equation, they are equilibrium temperature distributions. And again, we've seen with separation of variables that everything evolves to the equilibrium temperature distribution. So the question is, what do the equilibrium temperature distributions look like on, say, a square or a rectangle? So in this case, here's what I want to do. Again, things are going to get much, much, much more complicated. So here's 0 to L, here's 0 to H. This is my domain. I am solving this equation. And let's impose some boundary conditions. Let's say that at the top of the box, I have some prescribed temperature that is a function of x now, right? It has to go all the way across the top. Similarly, at the bottom of the box, I have, x comma 0. X is the first variable here. X comma 0 is another function of x. Similarly, on the left and right sides, I'm going to prescribe that you have a function of y. So here, you can imagine this as a big flat plate where I'm fixing the temperatures on each of the boundaries of this thing. And so here I have u of, 0, y is equal to g1 of y. So this is already a very complicated problem, right? It's much more sort of obtuse than the previous examples. I have to solve a partial differential equation in space, inside, and I have to match with 4 different boundary conditions. So the question is, how do you actually solve this? Well, here's what you do. You do a couple different separation of variables. So the first thing you're going to do is you're going to write the solution to be u1 of xy plus u2 of xy plus u3 of xy plus u4 of xy. Okay, so I decompose it into 4 different solutions, again, using the principle of superposition. But what distinguishes each one of these? Well, u1 is going to be given by solving the Laplace equation, all of them will solve the Laplace equation. It's a linear equation. You can check the linearity property. And here's what we're going to do. This one is going to keep this boundary condition. So u1 of x comma 0 is equal to f1 of x. But all of the other boundaries can be taken as homogeneous, as 0. u1 of 0 comma y is 0, and u1 of L comma y is 0. Okay, so u1 carried just one boundary condition. Then u2 is also going to carry only one boundary condition. So let's take this one. Let's go counterclockwise. So u2 of, L comma y here, my bad. L comma y is equal to g2 of y. And the other ones are going to be 0. Okay? You can probably guess what's happening here. Then let's do u3 of, it's going to take this boundary condition, x comma h is equal to f2 of x. And the rest of them are going to be 0. And finally, u4 of 0 comma y is going to be g1 of y. And the rest will be 0. Okay? So in some sense, you can kind of think about these as initial conditions in time with 0 boundaries everywhere else. So take a look at what happens here, though, right? Your solution is always going to solve the Laplace equation. And if you sum up solutions to the Laplace equation, they still all solve the Laplace equation due to linearity. Now, this boundary condition is enforced just by u1. These ones all give you zeros on the boundary. This boundary condition is enforced by u2. These all give you zeros on the boundary. This one by u3, the others give you zeros. And this one by u4, and the others give you zeros. So you got 4 PDEs to solve with 4 different boundary conditions. You put them all together using the principle of superposition, and you get a solution to your Laplace equation in the square. So you can already feel it spiraling out of control, right? You were probably thinking in the past 3 videos that this is easy, and what's the point in learning all this, Jason? This is sort of trivial. Of course, the complexity has just stepped up, and all that we did is increase the dimension of the domain by 1. People consider the Laplace equation in any dimension, on any domain. This is the easiest possible domain in the second to easiest dimension. Okay, so I hope that you can appreciate how complicated this is going to get. I am only going to solve this for u4, okay? I'm going to leave the rest of them as exercises for you. And if I was your professor, I would assign those as homework problems. So I would love to see somebody actually solve this. So, solve for u4. Well, what do we have? We've got the Laplace equation, and then plus boundary conditions. Okay, just because there's 4 boundary conditions, I don't want to write them all out because it's a lot of work. But you know what they are. I'm imposing this left boundary right here is g1 of y, and the rest are 0. Okay, separation of variables. We're getting good at this now, right? But here's the thing, separation of variables is going to come in a different form. Now I have x and y, not x and t. Let's, again, using Haberman's notation, the textbook that I've been following here, I'm going to use h of x and phi of y. And here's what my boundary conditions look like. Well, h of L, which would be in L, that's this one, is 0. Phi of 0, which is this one, and phi of h, which is this one, these are all 0. And then we've also got the last boundary condition that we will have to impose at the end. Okay, so what does my separation of variables give me? I get phi of y times h double prime of x plus h of x phi double prime of y is equal to 0. Why? just sum of second derivatives, right? So second derivative in x, that gives me 2 derivatives in h. Second derivative in y, 2 derivatives in y. Slightly different than what we had previously, right? Again, you can move this stuff around and you get the following here. You get h double prime over h is equal to minus phi double prime over phi. H is a function of x, phi is a function of y. The only way that these two things can be equal is if they are constant, and I'm going to say let this equal to lambda. You'll notice that I chose lambda instead of negative lambda here because, again, I know what's going to happen. It wouldn't matter. You could put a minus lambda. You'll see that everything floats through, and your answer should be exactly the same as mine if you do it correctly. Okay, so you get two equations. H double prime is equal to lambda h, and that has boundary condition h of L is equal to 0. And you get the second equation, phi double prime is equal to minus lambda phi, where phi of 0 is equal to phi of h, which is equal to 0. We actually solved this one already. So we solved 2. So we solved 2 already. This is basically what comes out of regular separation of variables. And essentially you get phi of y is any constant multiple of sine of n pi y over h for any value of for n from 1 to infinity. And this also drills down the value of lambda, right? Because it has to be n pi over h squared. So that means that lambda equal to n pi over h squared gives you h double prime is equal to n pi over h squared h. No negative here anymore, right? This is the difference in the two equations. So in this case, you actually get hyperbolic cosine and sine. So in this case, I'm going to do some fudging around. I'll explain in a second. This just makes the boundary conditions easier to implement, okay? So you get n pi over h x minus L plus C2 sinh n pi over h x minus L, okay? So maybe you don't like what I did here. The hyperbolic cosine and sine, these are the same as, e to the square root of lambda x plus a multiple of e to the negative square root of lambda x. We like to use hyperbolic sine and cosine, kind of looks like sine and cosine. It makes things a little bit easier. And also, you'll see that I shifted the solutions. Why did I shift them? Well, I shifted them just because I have a boundary condition at L to impose, this is just going to make it easier. If you didn't shift it, that's fine. You'll get the same answer. It'll just be way, way uglier. These are homogeneous equations in space, right? It doesn't matter what spatial point I'm at. I can always kind of move around. I have a symmetry, a translational symmetry almost. And so I can always write the solution as x minus L here instead of just x. I'm just shifting things over. If you didn't do the shift, that's fine. Your solution is going to be ugly, but it'll be technically the same as mine. Now, the point here is to impose the boundary condition. Impose h of L is equal to 0. And essentially what this gives you is gives you C1 is equal to 0, which tells you that h of x is all the constant multiples of sinh n pi over h x minus L. Okay? And so we can actually put this all together and we can get what the solution just for U4 is. Remember, this is all we're doing. We're just doing one. So think about how much work this is, right? So U4 of x and t, or sorry, x and y this time, pardon me. You get this huge series representation. Let me write it on the next line just so that I have enough room. N greater than or equal to 1. Now we assume that the solution was h of x times phi of y. So you get all the possible constants after evoking the principle of superposition. Sinh n pi over h x minus L. Again, if you didn't do the shift, you would just have like annoying multiple terms in here, coches and sinh. So this is just simplifying notation. And you can do the same trick whenever you impose the other boundary conditions if you'd like. And then times sine n pi y over h. So wiggles in space, these sort of exponential growth and decay in the x direction. Okay, wiggle in one direction, exponential growth and decay in the other. Now here's what I'm going to tell you. If you do the other three cases, here we have sinh and sine. You're going to get all other combinations. You're going to get sinh and cos, you're going to get cosh and sine, and you're going to get cosh and cos. 4 possible combinations, 4 different solutions. So if you put together the whole solution, it's 4 infinite series of all possible combinations of sinches and coshes and sines and cosines. And then finally, we have one more boundary condition. We have this. 0 of y is equal to g1 of y. All right, so you have some sort of fixed boundary over here on the side of your plate. And this tells me that if I set x equal to 0 in this thing, what do I get? I get g1 of y. So set x equal to 0, g1 of y right here. This is equal to, all right, let's take a look at this. The sum from n equal 1 to infinity, Cn, sinh of, okay, so x equal to 0, so I get minus n pi L over h sine of n pi y over h. Don't be fooled. It looks ugly. It's very complicated looking. But it's still just a sine series. Right? But this piece right in here is all the coefficient. So therefore, by what we've learned about sine series, each coefficient is now going to be, so you have this minus 2 over L, but you also have to get rid of the sinh term, or sorry, 2 over h, pardon me. So you have minus 2 over h, sinh minus n pi L over h. This horrible term, but it's got to go in there because you got to isolate the CNs. And then the projection onto each sine mode. y over h dy. So it's ugly, right? It's really, really ugly. And you're going to get some more ugliness whenever you do it over here. But even though it's ugly, even though it's a pain, you can do it. That's what I want you to see. You can solve this thing. It just takes a lot more work, right? So 1D, pretty easy, at least, with the boundary conditions that we considered. It's at least manageable for us. Here, it's manageable, but it takes some accounting, right? You have to be careful. You have to divide this up appropriately. And the reason we divided it up is because it made the boundary conditions easier to handle. You don't want to have to impose all these boundary conditions at once, or else you just get these huge exploding series. You'd like to divide it into problems that can be handled. The other thing I want you to see here is that this Laplace equation is solved now by infinitely many solutions. Remember, the Laplace equation is the equilibrium temperature distribution for the two-dimensional heat equation in this case. What we just saw here is that there are infinitely many solutions. They're only solutions of space and space, right? X and Y. These are all equilibrium temperature distributions. So that means that there are infinitely many of them. Unlike, say, with Dirichlet conditions where everything goes to 0, you can have very, very complicated behavior on these high dimensional domains. Okay, with that being said, in the next lecture, we're going to take a look at the Laplace equation. Again, we're going to solve it in 2 dimensions, but this time on a disk. So we're going to use polar coordinates. I'll see you all in the next video, everyone. Thanks for joining me.